Hello, everyone. This is the third lecture of my course on program synthesis and the ARC challenge. Yesterday, or in the last lecture, we have talked about formal languages and grammars and generally some tools that are useful for doing program induction. And today, we look at the main problem, really, of program induction, which is the problem of how to actually search this massive space of possible programs that we have defined with our context-free grammar or some other language, some other grammar. And we'll look at a series of strategies. So today we'll focus on symbolic strategies for search. We'll look at enumeration and how to do it smartly. Some Bayesian approaches like MCMC, particle methods, and a tool which is not strictly search but can help in finding good programs. And tomorrow in the next lecture, we'll look at neural and neurosymbolic search. So various approaches that involve neural networks. So let's start thinking about this. So what we talked about last time was how to define a space of programs. And the tool that we defined to do that is probabilistic context-free grammars plus a compositional interpretation function. We might care about other kinds of grammars as well. For instance, often you need some mild context sensitivity, which is useful, for instance, to make sure that variables are only defined in certain blocks of code. You can also use, instead of a bespoke domain-specific language defined by a context-free grammar, a general purpose language like Python. And we'll see more of that tomorrow when we talk about, or in the next lecture when we talk about neural methods. To do program synthesis, we need to find a program in the space defined by whatever language or whatever grammar you are using that fits the data. Of course, there's other kinds of program synthesis, but the one that we'll be focusing on is programming by examples, where you have some examples and you need to find a program that fits them, because that's the one that's most useful. That's the setup for the ARC challenge. So in this case, to do the kind of program synthesis we care about, that is the task you need to solve. This poses a massive problem, which is the problem of searching the space, which is, generally speaking, an infinite space, and with a very spiky reward function in terms of performance on the set of examples that we want to fit. By which I mean that a small change in the program can make a huge change in how well it fits the data. I will present a pretty partial and personal selection of examples, but I hope it's somewhat representative of the literature. If you think I missed anything important that is useful for the ARC challenge, then write me an email or send me some feedback in the feedback form on the website. So let's start with just some useful concepts, which are also going to be useful in the coming lectures. First of all, the distinction between a domain-specific language, which I will call DSL, and a domain general language, which I will call DGL, although really nobody uses DGL for some reason. So a DSL is a language where essentially you manually specify a smallish set of conceptual primitives. What counts as smallish set? Well, it depends on your application. This is what the ARC folks have to say about this. The DSL, for instance, for the ARC challenge, is designed to encapsulate common concepts such as rotation, mirroring, and other grid transformations that frequently occur in ARC tasks. So the idea here is that you have to be careful about selecting a set of primitives, conceptual primitives, that lead to kind of nice programs when they fit the examples. Nice could be, for instance, short programs or understandable programs, and so on and so forth. By defining a set of primitives or basic functions that perform these transformations, solutions can be synthesized by composing these primitives into programs that solve specific tasks. So this is essentially what we talked about earlier. Once you define these primitives, these interpreted primitives in your language, you can put them together according to rules defined by the grammar that then allow you to build unboundedly complex programs. Program synthesis in this approach involves searching through possible compositions of the DSL primitives to find programs that correctly transform input grids into their corresponding output grids. This search can be brute force or more sophisticated, but the idea is to leverage the DSL to build task-specific programs efficiently. So once you have a good choice of primitives, of course, that also makes this search easier. We'll see some examples of that in the labs, in the programming labs, in the notebooks. On the other hand, a DGL is just search in a system that can handle complex natural language, for instance, LLMs, or has a very rich inventory of operations meant for generic computation, for instance, Python. So it's not a language that is built specifically for solving, for instance, arc tasks. So that was the first distinction I wanted to talk about. And now there's a distinction between deduction, induction, abduction, and transduction, which is the new arrival in the family, so to speak. It's quite rare for a new concept to come about and fit so nicely into such an old categorization system. So let's start. So deduction. In deduction, you reason two conclusions from some premises using logic. Prototypically, this is good old-fashioned artificial intelligence. Induction, you go from a series of observed instances to a general rule that kind of tightly fits the set of observations. For instance, the sun rose every morning in the past year, to the sun always rises, which is the general rule, to the sun will rise tomorrow, which is an instantiation of the rule for the specific case of tomorrow. Abduction, you infer the best, in some sense, explanation given data. So what counts as best depends on the specific application. It could be conceptual simplicity. There can be other theoretical desiderata. For instance, the sun rose every morning in the past year, to some explanation for why the sun rose every morning in the past year. For instance, the solar system is so and so, to the same conclusion as we had for induction, but going through a more theoretical generalization. So the sun will rise tomorrow. And then transduction, you go straight from observations to predictions for a new observation. So you don't do this middle step that we did for induction and abduction, where you find a generalization and then you reinstantiate it for a specific other instance. You just go straight up from a set of observations to a new observation. Simply, the sun rose every morning in the past year to the sun will rise tomorrow. How do you do that? Well, that depends on the specific context. But you can. There's lots of literature in computer science for algorithms that do this kind of thing. So that is the distinction. Sometimes I will say program induction, and by that I mean what some people call program synthesis and what I generally try to call program synthesis in the course. But really, I find that a more proper name for this should be program abduction, since you're not necessarily finding a tightly fitting generalization extracted from the data, but often a more substantial theory, which is the best explanation for the data. So I think that should more properly be called abduction rather than induction, but that's the term that has been introduced and it stuck. So let's start looking at ways that you can actually search the space of possible programs to find one that fits your data in a programming by example program synthesis setting. Let's start with enumeration. So how do you do enumeration? Well, you do basically a search in the space of programs, and this is the general approach. You start by specifying a probabilistic context-free grammar. You don't really use the probabilistic bit here. So a context-free grammar is enough in this case, and an interpretation function. The interpretation function is also not strictly necessary, although we will see in a second that there are variations of where you need it. Then you enumerate the productions from the context-free grammar. You evaluate each production on success in the task. And for instance, you stop at the first production that you find that fits your data, which you would consider the minimal formula or the minimal program that correctly fits your data. If you put a lot of emphasis on simplicity, you might think that this is the best explanation for the data. From the ARC website, This was the first domain of solutions that started working well in the original hackathon competition in 2020, hosted by Lab 42. It involves searching through a massive program space in discrete step-by-step manner. So this is a very simple algorithm, but if you optimize it and you make it really fast, then it can perform quite well. So what is the main problem? You probably have guessed it by now if you are familiar with anything like the problems that we are looking at. It's combinatorial explosion. So once you start enumerating all the programs in order, even for, well, depending on the number of primitives you have and exactly how your grammar is set up, but generally you get a combinatorial explosion of potential programs, even at very small depth. So let's see what the situation is for a specific example. Suppose that we have this CFG, which is a fragment of propositional logic. So you have S, and S goes to P, or it goes to Q, or it goes to S and S. There's a typo here. So or it goes to not S, or it goes to S to S. So you have the pair propositions, the atomic propositions, the conjunction, the negation, and the conditional. And so the way that enumeration would start, and this is actually a specific kind of enumeration, which we call top-down enumeration. And we call it that because you start with the top formula, with the S in this case, your starting symbol, and then you apply all the possible rules in every possible order. So you make all the possible generations of this from this grammar in the way that we have seen in the previous lecture. So for instance, you apply the first rule here, and that gets you to P. And now you're left with just terminal symbols, and therefore there's nowhere to go, which I indicate as a light gray color. Then you can go from S to Q, and then you're also left with just terminal symbols. Then you can apply not S, and that gets you to, well, just not S, because your initial formula here was just, your initial formula was just S. And then from not S, you can apply Q, that gets you to not Q, S to S. So here I'm always replacing the first non-terminal. So S to S gets you to not S to S, not S, not S, if you apply negation here, and so on and so forth. So the circles which are not gray, you could continue producing from those. Now, this is just with 2 levels of depth, but if you increase even just to 3, you start noticing this massive explosion of the number of possible formulas. And that's a problem because, well, the true formula might actually be quite deep in this search tree. So we need ways to branch to prune some of the trees as soon as we can tell that they are not useful for what we want to do. So one thing you can do to start this pruning, and then we'll see another strategy, you can use deductive rules that can help you eliminate partial proposals. So how does that work? Well, for instance, we can remove double negations because we know that they are going to be synonymous with a simpler formula which you have already encountered. For instance, if you apply the strategy of removing double negations from in the case that I have just shown, you start seeing that you exclude some branches, which means you don't have to keep exploring those branches any further. So here, for instance, you can exclude not S, which would then in itself start branching out into many formulas that now we don't need to search through. Okay, so that can reduce the search space substantially if you have a good rich set of deductive rules to help you reduce the search space. There's another strategy which is I think very elegant and very nice, and that is important if you have multiple semantic types in your system. So suppose that you are trying to search the body of a lambda expression. So you need to search for an expression to put in here, which comes from this grammar. So you have expression, and you can replace that with x, which is going to be a variable of integer type. Then you can say expression is greater than expression. You can just have a bare expression. I think that's a typo. Then you have expression and expression. You can have a 1, and you can have expression plus expression. I think this is supposed to have a negation there. So just to give you a sense of how this works, you can have expression here, and then you can generate, just like we did earlier, a 1, or you can generate just an x, or you can generate the negation, and then, for instance, fill expression there with the x, and so on and so forth. But the important thing to note here is that even though the grammar is not sensitive to these distinctions, so everything is an expression, semantically we have objects of two different types. We have Boolean values, for instance, the arguments that the conjunction takes, and we have integers, for instance, the arguments that the greater than operation takes. So these symbols, once they get interpreted. And we want this body in the lambda expression to evaluate, once you filled in a value for x, we want the whole thing to evaluate to a truth value. So we want this to be a predicate, something of type et, which takes an individual for x, which we fill in for x, and returns, once evaluated, a truth value. So if we just do the search with the grammar as it is, you have a problem almost immediately. So even with just, I think this is 3 levels of depth, you get this massive, really quick combinatorial explosion. So what we can do is we can check the type of each partial proposal, and then we eliminate the proposals of the wrong type. Now, we can tell what the partial proposals, what the types of the partial proposals are, just based on the operators that they contain. So for instance, if we have a proposal that contains a conjunction, we know that that whole thing is going to be of type Boolean, even if we don't know what the values for the expressions is going to be in all of the branches. And so we can exclude, if we know that this expression has to be of type bool, then we can already start excluding values one step in. So for instance, if we know that this is of type bool, then we know that it's not going to be 1, it's not going to be x, because x is an integer, and it's not going to be expression plus expression, because we know that whichever way you fill in the values for these two expressions with rules in the grammar, this whole thing is going to evaluate to something of type integer. And so this really reduces the space of the search space massively. So for instance, we go from this, which is well, unmanageable, to this, which is a massively reduced search space. So this can work very nicely again. So you can exploit the semantic types of the expressions, which you can determine even for partial, not completely filled in formulas, to reduce the search space, even when your grammar doesn't care about the semantic types, like the grammar that we looked at a moment ago. So that was the top-down approach to searching, where you start with the starting symbol and then you apply every rule in every possible combination to get to all kind of the successive sentences that you can produce in the grammar. There's also a bottom-up approach to search. So what is bottom-up search? What problem is it solving? The problem is that with top-down search, we cannot evaluate expressions until we reach a leaf. So we need a full expression, by which I mean an expression, a sentence which doesn't contain any non-terminal symbol, before we can run our interpretation function and evaluate the meaning of the expression. This is not ideal, because there are things we can exclude some expressions just based on their components. So if we could tell what the meaning of the components is, we could exclude them before we have to search through all of the possible subtrees. So the alternative is to do it bottom up. How does it work? Well, you start with the terminal symbols that are in the grammar, and then you combine them in every possible way that the grammar allows. For instance, with the little propositional logic that we had earlier, you can start with P, and then you can apply, for instance, the negation rule of the grammar, and that gets you to not P. You can also combine P and Q in various ways. For instance, if you combine them with the rule for conjunction, you can get P and Q. Of course, this also has the problem of combinatorial explosion. For instance, this is what happens if you increase the depth by just 1 with the formula that compared to this search tree. So this is just depth 2. So how can we improve the search tree with the bottom-up search? Well, at each step, you just remove the expressions whose meanings you already found. So you have completely interpretable expressions at each step of search. So you can keep track not of the expressions, but rather of the meanings of the expressions that you already, so you can keep track of the meanings for which you already have found an expression. And then whenever you encounter a new expression, you check whether its meaning is already in your library of meanings that you already have an expression for, and if it is, you just stop searching, you stop involving that expression in the future combinations to produce new formulas. So for instance, in this case, here we have that we already have an expression for Q and Q, which might have been, which is just Q, which is the same as just saying Q, which is here. And so we don't let that become the parent of any other expression. We just stop the search there. We just keep working with the formulas for which we didn't already have a meaning. And that is a kind of big improvement because it reduces the space from this to just this. This is, of course, a very simple case because there is only 16 possible truth tables you can build with 2 propositions. But the problem is that often you don't know in advance how many possible semantic values there are in your system, and that's when this is really convenient. Okay, so that was top-down and bottom-up search with a couple of tricks for how to make them quicker. There's, of course, other very smart algorithms for how to do enumerative synthesis. For instance, this is an example which is discussed in this really nice course by Armando Solá Lezama, which is an introduction to program synthesis. And it comes from this paper, Synthesis for Unification, from 2015. And it's called STAN, which stands for Synthesis through Unification. So how does it work? Well, you start with a list of input examples, just a bunch of examples that you want to fit in a programming by example setup. Then you enumerate your from your grammar in one of the ways that we have discussed to find program for at least some of the examples that you care about. If it fails on some, you can either improve the program, so you can find a better program and then go back to the beginning, or you can find a different program, so you can run the whole algorithm again on the programs that your first proposal fails on, and then you can merge the new program that you found that solves the algorithm, the examples on which that you had initially failed to find a program for, with the old program that solves the first set of examples. And then at the end, you get a kind of combined program that can account for the examples that you initially failed to find a program for. So that's one example of many fancy approaches to doing program synthesis through enumeration. So that's a kind of nice approach, nothing wrong with enumerating, but of course there's other approaches. So let's look at a more probabilistic one, Bayesian inference and Markov chain Monte Carlo approaches. So the enumerative approach explores this space exhaustively. And it is good if you want to find things like minimal formula with a guarantee that you found it. But what if the program is stochastic or there is noise in the observed examples? So there might be a formula that actually fits the example very well or better than a shorter formula that fits them a bit worse. So there's this tension between the complexity of the formula and how well it fits the data. And there you need to explore beyond just the minimal formula that fits the data that you have. Perhaps we don't want a single program, but we want a whole distribution so that we can consider many formulas that fit our data. Or maybe the programs we want are concentrated in just a few areas of grammar space, so we don't want to exhaustively enumerate all of the possible programs, but rather we want to get to that part of the language produced by our grammar and then search around there for a good set of programs. So Bayesian inference is a possible solution to these challenges for doing program synthesis. So let's take it from the start. What is probability? I'm going to go through this very quickly because, of course, this is not a probability course, but I think this is helpful because people tend to get a bit confused about this. The answer is that there is no single answer to this question. There are at least 3 answers, and the way that they fit together is a question for philosophers. But if anyone tells you that the answer is easy, then they are wrong. So one answer is that it's a feature of systems in the world itself. So for instance, the dice behavior over many rolls. That is not about how you feel about the dice. It's just something about the dice themselves. Another interpretation of probability is that it's a degree of support between propositions. For instance, given that it's raining, we'll probably get wet. So that is not about my personal belief, or the level of belief that I have in a proposition. It's a relation between propositions themselves. And then the third interpretation is the strength or degree of a belief, what philosophers also called credence. For instance, I think George is probably at the party. That's expressing the degree to which I believe a certain proposition. And so in the context of the following, I will write PA for the credence of A, PA given B. So I read the pipe symbol as given in that context, or the credence of A given B. And in general, they are not the same thing. So that is an important point to understand if you have never seen probability. I'll give you an example to clarify. The probability that X flies, given that X is a cocapo, is high, but the probability that X is a cocapo, given that X flies, is low. So the cocapo is this adorable bird, which is an extremely rare bird. And so if all you know about this object is that it flies, the probability that it is a cocapo is very low. But you know that if it is one of these really adorable rare birds, then you know for sure, well, you with a very high level of credence that it flies. So Bayes' theorem is a very neat way of converting one conditional probability into another. You also need one more ingredient, but we'll see that in a second. So the Bayes' theorem has 4 ingredients. The posterior, which is the probability of some hypothesis given the data you observed. The likelihood, which is the probability of the data you observed given the hypothesis. The prior, which is the probability of the hypothesis before you observed any data. And the evidence, which is the probability of the data regardless of which hypothesis you're considering. There's a lot of subtleties here that I'm not really going through. For instance, the temporal interpretation of Bayes' theorem in terms of the update of a system with beliefs is not the only interpretation of Bayes' theorem. Bayes' theorem is just talking about the relation between probabilities. The dynamic interpretation is just one of the interpretations. The interpretation in terms of credences is also not necessary. Bayes' theorem just follows very directly from the definition of conditional probability. And so this is true also in the other interpretations of probability, but it's a very natural expression if you are thinking about the ways that we update beliefs given some data. And so what it says is that the posterior, so the probability of the hypothesis given the data, is equal to the likelihood, the probability of the data given the hypothesis, times the prior, which is the probability of the hypothesis, and then divided by the evidence, which is the probability of the data. The important thing to note here is that the posterior is a function of the hypothesis. It's not a function of the data. You can consider the data as fixed. So the evidence doesn't change depending on the hypothesis. It's independent of the hypothesis. And so really it's just in a certain perspective, it's just, you can see it just as a normalization constant for this likelihood times prior. Of course, it has important roles to play in things like model comparison, but that's not going to be, we're not going to go through that right now. So what is Bayes' theorem saying conceptually? It's saying something actually quite surprising about the world, or rather every possible world, but nonetheless surprising. It's saying that the degree to which you should believe a hypothesis, given that you observe some data, only depends on two things. The first one is the degree to which you believed the hypothesis before you observed the data, at least in the dynamic interpretation of Bayes' theorem. And the second is the probability that that hypothesis would have generated that data. The most straightforward consequence of this is that if you assign probability 0 to a hypothesis before observing the data, then there's no matter what the data is, you're going to also have probability 0 for that hypothesis after you observe the data. And the second thing is that given equal prior for two hypotheses, if one hypothesis is more likely than the other to generate the data that you saw, then you're going to attribute to that hypothesis also higher probability after observing the data. And then, of course, if the data could never have been produced by that hypothesis, so it's produced by that hypothesis with probability 0, then it's also going to have probability 0 in your posterior. So you're going to attribute no credence to it after observing the data, if you're a perfectly rational agent anyway. So why is this relevant to us? There was a lot on probability and update of beliefs, but it turns out that you can apply Bayes' theorem quite directly to the case of inducing programs from examples. How? Well, what are the components of our program induction setup? We have an interpreted PCFG, and you can think of the productions from this PCFG as the hypothesis, as the possible hypothesis that you are considering. So each sentence is produced by the PCFG is a possible hypothesis. It also gives us a prior over this hypothesis. What's the prior? It's just the probability of that production in that PCFG. Then we have some observations, and those are generated by some program. We don't know exactly what it is, this H, this hypothesis. And what we also need is the likelihood function, which tells us what is the probability that each of the possible programs, i.e. each of the possible hypotheses generated by our PCFG, would have produced the examples that we saw that we want to find a program for. And so we can do Bayesian inference to get the probability of the hypothesis given, i.e. of the program, given the examples of that we saw that were produced by the program. So the PCFG is the space of possible programs, gives us a space of possible programs. The hypotheses are the sentences. The prior is the probability assigned by the PCFG to each sentence. The observations are the data for learning, so the examples that we observed that we are doing program induction on. The hypothesis H is represented in our CFG. The likelihood tells us how the program generates the data. This can be probabilistic. And Bayesian inference gives us a distribution over programs. So Bayes' theorem again. Once again, so the posterior is the probability over productions conditionalized on the data that we observed. The likelihood is the probability of the data given each possible production. The prior is the probability of the productions in the PCFG. The nice thing about the prior that is given to us by the PCFG is that, generally speaking, simpler representations have a higher prior. So we have for free this nice simplicity inductive bias. There are three ways that probabilities enter the picture in this context. One is the likelihood function. So the fact that the hypothesis can generate data not necessarily deterministically, but also in a stochastic way. Another way is that the prior assigns probabilities to productions. And then we can also have stochastic primitives. So we can have conceptual primitives, the interpretations of some terminal symbol in our context-free grammar, that when evaluated produce different things according to some probability distribution. So I'm gonna just put this on the screen. You can have a look. You can do this as an exercise. Do it at home if you would like. I'm not gonna go through it in detail because I think it's just a matter of filling in the values here. So what I want to emphasize here is that in order to calculate the Bayesian evidence, so this value here, you need to sum essentially the numerator of Bayes' theorem, but for all the possible hypotheses that you have. And in general, doing this sum, which is an integration if your hypothesis space is continuous, is not possible except in the simplest possible cases. So when you have just very few hypotheses. So either you have an analytic solution for this, or you need to approximate it in some way. For instance, we could not sum over all of our expressions in our PCFG, which is the set of our hypotheses. There's infinitely many of them. We need an alternative approach. So what we would like to do is we would like to get posterior samples, so samples from the posterior that approximates our posterior, even if we only know the prior and the likelihood, but not the evidence. So we can calculate the prior and the likelihood, that's easy, for specific hypotheses, but we cannot calculate the evidence, so we would like to get an approximation to the posterior, a sample approximations, just given our ability to calculate the likelihood and the prior. And that's what Monte Carlo Markov chain algorithms give us. So let's see how it works. I'll explain it with an analogy. Suppose that you are on a ship on a lake. And you can do some things. You can poke the bottom of the lake with a stick. So for instance, here you can check the height by seeing how far the stick goes. And that's going to give you a certain height. And then if you're deeper, if you're at a point where the water is deeper, then you'd get a different height. And so you can determine the depth of the water at any point. The problem is, the challenge is, you need to write down a list of points on the lake with a frequency proportional to their depth. How would you go on about doing this? So that's basically our challenge, but instead of depth, we have this likelihood times prior value that we are trying to get samples from. So I hope you see how this problem of the sheep is equivalent to the problem of finding the of generating samples from our posterior distribution. So this is one solution to this task, which is the Metropolis-Hastings algorithm. How does it work? It works like this. You start at any point, which we call P current. Then you take n steps. And at each step, you try a different point proposed following a certain proposal distribution. So if you're the sheep, you might have some kind of probability of moving left or right on the lake, according, for instance, to a normal distribution centered around your current position. The important thing here is that the proposal can depend on your current position. Then, if the depth at the proposed position is greater than the depth at the current position, so you need to keep track of both. If that is the case, so if you get a deeper point, you move to the proposed position every time. So you set probability of you set P current to P proposed. If it's not, then you might move or you might not move. You move to the proposed position with a probability proportional to the proportion of the depths of the two positions. If they're almost the same, you move with high probability. If the probability of the if the depth of the proposed point of the proposed new location is much lower, then you move with a low probability. Metropolis-Hastings is just this, but instead of depth, we have the unnormalized posterior, so prior times likelihood. These things are slightly more complicated if you have an asymmetric proposal distribution, which means that you don't move to, in the case of the sheep, just to visualize it, you don't move to so if you're in a P current and you move to P proposed, that if that is not the same as the probability of going from P proposed to P current, then you have an asymmetric proposal distribution and you need to adjust with this according to a certain ratio, but you can just have a look and make sense of it on your own. Turns out that if some pretty weak conditions are satisfied, in the limit of infinite samples, the distribution of the samples converges to the true posterior distribution, which is very neat because this is a very simple algorithm, but nonetheless we have this kind of nice behavior in the limit. This is in the limit, but then of course, how long does it take to get to a good approximation? Well, that depends on many things. For instance, if there's large, long valleys of low probabilities in between areas of high probabilities, where I'm talking about distance in terms of steps of the proposal distribution, then then it might take a very long time to move between these nice areas of high probability. So, but nonetheless, MCMC is a way of getting samples from the posterior without knowing the normalization constant, which is what we couldn't get. So how do we use this for finding a good program in a program synthesis setting or a good distribution over programs? Well, here's one possible way. You can use MH to infer Metropolis-Hastings to infer a posterior over models given observations. And the big challenge is to find a good proposal distributions for trees. So you have a current tree, which is your P current, and you want some function which proposes a new tree that you can move to. So you start with the current tree, then you select a subtree of your tree, and then you regenerate that subtree with the same CFG that you had and an auxiliary probability distribution, so an auxiliary probability component in your PCFG. This is the subtree regeneration proposal algorithm proposed in Goodman et al. 2008. And then you just accept with the probability here in the on the screen. The complexity of the expression is due to the fact that this subtree regeneration algorithm does not define a symmetric proposal distribution. So this is just one example of a proposal distribution for programs. You could define many others, but in general, the problem of this approach is that the search is not guided, i.e. the proposal distribution, at least in the basic case, is not taking into account where it needs to go. So it's not taking into account the data that it is trying to fit. There are also variations of this. We'll see some in the next lecture, where you combine the search distribution with a neural network, for instance, that takes into account the data to generate a new potential program. So that was it for the Metropolis Hastings approach to program synthesis. And now let's look at sequential Markov chain approach. And this is a pretty intuitive approach. Here I'm showing a plot from Alvarez 2017, sequential Monte Carlo methods in Bayesian joint models for longitudinal and time to event data. I thought this was a kind of nice, simple illustration of the main idea. How does it work? Well, you start at T0 with a bunch of initial samples from your context-free grammar. And you can generate them however you want. You can just sample from the PCFG, or indeed, if you have some other non-context-free grammar, you just samples from that. You just take samples from that. Then you evaluate, okay, how well does each of these samples fit the data that I need to make sense of, that I need to explain. And then you give them a weight depending on that. So programs that make more sense of the data, that fit the data better, are gonna get a higher weight. And then you resample with a probability proportional to the weight that you calculated for each of the programs. So programs that fit the data better are going to be sampled more often than programs that don't. And that's called the resampling step. And then we have another step, which is the perturbing step. And what you do is you take each of the samples that you got and you modify them independently. So once again, here you have something like a proposal distribution, something that takes a sentence and gets you another sentence. And then you reweight, you resample, you reperturb as many times as you want. And if you do this enough, at the end, you have a distribution of particles which approximates the posterior distribution, or which approximates whatever measure you used for the weighting. Here's an example. Here's how you use this for program synthesis. So the value function could be, for instance, some learned value function that assesses the likelihood of success for the branch. It can be a neural network. It can be trained directly, for instance, on input plus proposal, or, for instance, on the error message from the REPL. So you can do really whatever you want in terms of the value function. And then the policy function, which proposes these variations on current particles, it can be symbolic, like subtree regeneration that we saw a moment ago, or it can be a neural network, for instance. This algorithm has been used for generating, for doing program synthesis. There's this paper from 2019 by Kevin Ellis and colleagues. Kevin Ellis is a big figure at the moment in program synthesis. He will come up again when we talk about program synthesis in the context of the ARC challenge in the last lecture. But this is of course an earlier paper. And what they do is they are given an image, and they want to find a program that fits the image. So what they do is they start with an empty program in this case, and then they propose a bunch of possible first components of the image. And then they reweight those depending on how well they fit the image that they are trying to approximate with the program. And then they sample from these images. They modify them, so they combine the sub-images randomly, and then eventually repeating this process many times, they get to images that fit the one that they are the one that was given to fit, as an example. Okay, that's it for the sequential Monte Carlo approach. And now, finally, I wanted to say a little bit about the library learning approach, which is a very nice tool that was developed fairly recently. It's a bit older than this paper, so there are papers before that use this approach, but Bowers et al. In just a couple of years ago published this paper, and also they published a library which in Rust that has a really nice Python wrapper, so you can really they make it very easy to do library learning. And the tool that they develop is called Stitch, and it works as follows. Suppose that you have a set of programs, and Stitch really only works if your programs are written in Lisp notation. So you have a set of programs, and you notice, okay, there's some parts of these programs which repeats across many of my example programs. And what will be nice is if we could extract this part that repeats, refactor all of these programs, so define a new function that consists just of the repeating bit, and then rewrite our list of example programs in a more compressed way, in such a way that they are semantically equivalent to our initial set of programs, but they are compressed because they use this function that we defined that repeats across many programs. For instance, in this case, we can define this function that just includes this bit that repeated across the three programs. And then we can rewrite these programs in terms of that function. So for instance, here lambda x plus 3 times plus 2 for 2, which means first you sum 2 and 4, then you multiply the result with 2, and then you add 3 to that. You can rewrite that using this function as just fn0 plus 2 for 2. And this is what Stitch does. It's really nice. So you can define some DSL, and you have a corpus of programs in the initial DSL that encode some set of observations. So you've already done program induction on these programs, on these observations individually. And then what Stitch does is it uses this corpus-driven top-down synthesis, and it finds new abstractions that compress the formulas that you found. And now you have a learned library with new abstractions. Why is this cool? It's cool because if your observations, not just the ones that you already have, but maybe the future ones that you expect to have to come to you in the future, come from a similar environment of programs, Then you can, using this library learning approach, you can develop a set of primitives from the data, which you can expect to be useful for inducing future programs. And that's really nice. I think this is still a kind of somewhat underappreciated technique. Some people have used it for ARC, but the paper is quite recent, and I think we'll see a lot more of it. Then the last thing I wanted to mention is ensembles. I just want to mention something that the ARC folks said about it. They said, this approach consists of piecing together existing publicly available solutions to correctly answer more tasks than any solution achieved alone. This is the approach that was used to get to the current high score. So that sounds promising, but then they add, one thing to consider in utilizing this approach, it's unlikely that an ensemble approach will be able to generalize to correctly solve tasks outside of the public dataset. If you've got your eyes on the grand prize, you'll want to create new and novel techniques. And I think people have really picked up on this suggestion because the 2024 edition has seen a lot of new ideas coming in the papers that were sent. So that is it for this lecture. If anything was unclear or if you have any questions, let me know, send me an email, put it in the feedback form. If you want me to go through something again or more clearly, let me know. And there's going to be a Jupyter notebook on the website where you can just see how all of these ideas, or at least some of them, are implemented in practice for program synthesis. All right, I hope you enjoyed it, and I'll see you for the next lecture, or rather, you will see me for the next lecture.